Hi everyone. This is our lecture video ending section 3.1. I am going to go over union and intersection notation. This notation is often used for sets of real numbers. So let's suppose that A and B are sets, and I drew a little diagram here. This is called a Venn diagram representing the sets A and B. So A is a circle. We're in this illustration, it's a circle, and B is also a circle. And it says here, for the sake of this illustration above, let us assume that A and B actually have some sort of overlap. So in that illustration, you can see that A and B, they have an overlap there. So the sets in the illustration above are represented by these circles. Now you'll notice that on the screen I have an A followed by an upside down U and then B. What exactly is this thing? That A with an upside down U and a B is read as A intersect B, or the intersection of A and B. It is defined by the following. So this is the definition here involving set builder notation. So A intersect B is the set of all elements X such that X is in the set A and X is also in the set B. Looking back at that Venn diagram, A intersect B is the overlap of the two sets. So anything that belongs in that overlap is said to be a part of A intersect B. Now up next is union. So how do you read this thing here, this A with a capital U followed by a B? This is read as A union B. The union of the two sets A and B is defined as the following. It is the set of all elements X such that X is in A or it is in B. The key word here is the word or. So the union of two sets, this represents basically everything here shaded in the black. Oopsie, that's supposed to be black. Everything here shaded in the black for these two sets, A and B. So if you have something is in the union, this means that it is in A or it is in B. Notice that I also shaded that overlap because if you are in that overlap, that means you're in A and you're also in B. So it satisfies this set builder notation. Sorry, it satisfies this set definition. So here I have an example where the union notation is used. Let's suppose I asked you to find the domain of this function, f of x equals x over x squared minus 4. Looking back at our lecture for 3.1 so far, we know that this function is undefined when the denominator equals 0. The denominator equals 0 when x equals 2 or x equals negative 2. The domain of this function using set builder notation is the set of all real numbers x such that x does not equal negative 2 and it does not equal positive 2. What does this domain look like using a number line? So if I were to draw this domain using a number line, I have to put parentheses to the left and to the right of negative 2 and positive 2. Why? We know that we can't plug in those two numbers, but we can plug in everything else. I can plug in anything to the left of negative 2. I can plug in anything between negative 2 and 2. I can plug in anything after 2 into this function. So our domain here, if we look at the number line, the domain is composed of three intervals. The interval from negative infinity to negative 2, the interval from negative 2 to 2, the interval from 2 onwards to infinity. How do I write the domain here using interval notation? Using interval notation, since we have three separate intervals as part of our domain, I have to use this union notation, which I did here for this problem. So let's go back to section 3.1. This is where I left off in last Thursday's lecture. Let's suppose you have two functions f and g with domains a and b respectively. The sum, difference, product, and quotient of functions will in fact create a function. On my left, I have how those functions are defined, and on my right, I have the domains of each of these functions. So if A is the domain of f and B is the domain of g, the domain of the sum, difference, or product of functions is the intersection of the domains A and B. Now, when we get to the quotient of two functions, this is where things get a little strange, but not too much. The domain of a quotient or ratio of two functions, it is going to involve the intersection of the domains of f and g, but we need to exclude the values where the denominator equals 0, because as you know, you cannot divide by 0 and get a real number. Let's take a look at an example. Let's suppose I gave you two functions, f of x, square root of x minus 4, g of x, square root of x minus 5. In part 1, you need to find the ratio of these two functions. So how do you do this? We know that the ratio of two functions is equal to a ratio of the first function divided by the second function. So this equals the square root of x minus 4 divided by the square root of x minus 5. And that's it. That's all there is to do for finding the ratio of those two functions. Now up next is the domain. This is where things are going to look a little weird, okay? Let me scroll back up to what we have. To find the domain of f of x over g of x, I need to find the intersection of their two domains, and I need to exclude the values where the denominator equals 0. Let's actually write out the domains of f and g right now. So for the domain of f, what do we know? So we have a square root function. We have to exclude the values where the square root of x minus 4 is negative. And that is going to be for anything that is less than 4. The domain of f then will be everything from 4 onwards. The domain of g, so for sake of example, I'm going to call these a and b, okay? You don't have to call these a and b like I am here. I'm just calling these a and b because I don't want to keep writing domain f and domain g over and over again for this problem. So for the domain of g, we should end up with all real numbers from 5 to infinity. If you look back at our 3.1 lecture and you follow your rules for finding domains of functions, you should end up with the same results that you have here, that I have here, for the domain of f and g respectively. Now the question is, what does that intersection look like? Let me represent this by number lines. So here's 4, a bracket, I draw an arrow. For the domain of g, here's 5, a bracket, and I draw an arrow. Now, where do these two sets overlap? These two sets will overlap where we have an overlap on the number line representation. It should be clear to everyone that the overlap between the domain of f and the domain of g is going to be from 5 onwards. So that overlap is going to be from 5 onwards. Now, this thing that I wrote here in the blue, it is not the domain of f of x over g of x, right? Why? Well, we know that if our function is square root of x minus 4, over square root x minus 5, I need to exclude any values where the denominator equals 0. For this set in blue, if I plug in 5, the denominator equals 0, so I have to exclude that, right? The domain of this function is going to be 5 parentheses to infinity. And now we are done with this problem. Alrighty, everyone, I will see you in the next lecture video, which will be soon.